No, I'm not doing take 3. We're doing take 2. Take 2. We're starting to unit 1.11 now. It's happening. It's happening. I don't care how stupid it gets now. It's happening. Here's what's up. This thing is called equivalent representations of polynomial and rational expressions. That basically means we're going to factor everything and then use our factored stuff to analyze things. We're not going to be doing anything new today. It's just taking the stuff that we've already learned from 1.7 through now and kind of putting it together. Okay? Putting it all together. All the wholes, asymptotes, inequalities, zeros, all of that good stuff is happening in one lesson. That's what we're doing. Got a polynomial here. It says find an equivalent representation. That means factor it. And then we're going to use the factored form and other things we know to sketch this graph. Cool? Cool. Great. First things first. This is an odd degree polynomial. Because the degree of the polynomial is odd, what do we know about it? What does that instantly tell us? The directions of the endings, yes. And they both did the fingers. They look like they're doing disco over there. They go opposite directions. Yeah. So because we have an odd degree polynomial here, our two endings point different directions, one up, one down. The leading coefficient is positive. So since the leading coefficient is positive, we say that this thing kind of has a positive average rate of change, essentially left down, right up. And imagine you were going to connect the two arrows with a straight line, like a dotted line in your mind. See that this dotted line that I'm not currently drawing would have a positive slope. There. And if it had a negative front number, obviously it would go left, up, right, down, so that you had a negative average rate of change. Cool. So that is what the edges of our graph looks like. Now, let's factor it. Very first thing you should always hunt for when you're factoring, JCF. This one has one. What is it? X. Very simple. Okay. We're going to pull an X out. Leaves me X squared minus 2X minus 15. Like that. And yes, there are two numbers that multiply to negative 15 that add to negative 2. So life is good. It factors quite easily. The two numbers that multiply to negative 15 and add to negative 2 are negative 5 and positive 3. Okay. If you hear me say something wrong or write something wrong, please catch me because I was goofing up left and right last period. X plus 3x minus 5. So then how many times does this cubic interact with the x-axis? All 3 times. And then so my question is, does my graph bounce at any of these x-intercepts? No, but how did we know that? No multiplicities that are even. There it is. No even multiplicities. So no powers of 2, 4, 6, 8, whatever on my factors. These are all odd multiplicities. No bouncing. Guaranteed we only have crossing. And because they all have power of 1, I know the ones aren't written, but because they're all a power of 1, all of my graphs are going to go through the x-axis, not graphs, all my curves. They're going to go through the x-axis in a linear fashion. They won't get fancy. They won't have any wiggle. Okay? Just going to go straight through, kind of straight. Wait. Wow, that sounded stupid. They're going to go right through almost in a straight fashion. Where, though? At this one, what's my solution? 0. Anytime you have an x outside of the parentheses in your factored setup, its solution's automatically 0 every single time. So we have x equals 0, and then it's just what makes the insides equal 0. So negative 3 and positive 5. Okay. Well, so these two numbers, the 5 and the negative, excuse me, the 3 and the negative 5, they add to negative 2. No, you're not dumb. You're not dumb. But anyway, it's whatever makes the inside of the parentheses equal 0. Yeah. We're good. So I'm going to try to get my x-axis to scale. There's a 5, and I'm going to try to go the opposite direction in the same scale. It's harder to do that. I'm not a lefty. No, because lefties push their pencils and pens rather than pull. So I was able to go this way, but it was hard for me to go the other way. Yeah. Did you know that I... Bet you didn't know that I knew that, though, did you? You know why? What you do as a teacher, if you want to get people that are left-handed, is like you save up. You know how I have a box of pencils over there for people that forget their writing utensils? What you do is you fill it with all of like the world's runniest ink pens. That way when lefties use them, they push ink all over their paper because it's funny. Who threw that paper at her? Hate crime. It was a hate crime. She can't help it. She's part of the 10% minority. Okay. Shh. Hey, nut jobs. Psst. We gotta do this. Left, down, right, up. So we said it's going to cross through. Cross through, cross through, cross through. There it is. So the directions do say to analyze this function. And that would mean, you know, where is it increasing, where is it decreasing, where is it concave up, where is it concave down, technically, where is it positive, where is it negative. And then we could also talk about symmetry. Now, without calculus, we're not going to be able to say exactly where our maximums and minimums occur. By that, I mean where the x values are. Is there a maximum somewhere between 0 and -3? Yes, there is. But is it going to be at -1.5? No, that's not how math works. But we know that somewhere in here there's a turning point. And we know that somewhere in here there's a turning point. So let's analyze it just visually. We don't need to write anything down. To the left of the red pen, what one word could you use to describe the graph?
Negative.
Increasing. Because you go from left to right, you're going up. So the graph is increasing from here to the tip of the red pen.
Wouldn't it also be negative?
No, it would be negative right here, but it's positive right there.
Oh, we're talking about like in terms of...
Yeah, to the left of the red pen. Yeah, piece of it is negative, yes, but just in general. To the left of the red pen, my graph is increasing. Between the two pens, my graph is decreasing, and then after the orange pen, increasing again. Now, without calculus, I don't know exactly where it happens, but I do know that somewhere here-ish, there's an inflection point. Somewhere here. I'm not sure where, but it's definitely... That is even too thick. It's here somewhere, okay? Like that. To the left of my pencil, would we say concave up or concave down?
Down.
This is concave down. This is concave up. There. Last question for you. Symmetry. And I'm looking for voices. I need everybody in the room to either say yes or say no to the answer to this question. You ready? Class? Is this an odd function? A handful of people said no. A handful of people are correct. This function is not oddly symmetric. Now, it has an odd degree, but that's not what I asked. I said, is it an odd function?
No, because it's at 5. It's not. And one's at -3 and one is at 5.
So what Sage is saying, and he's right, one of the ways that we know for sure that it's not odd is that the zeros are not symmetric around the origin. All odd functions are symmetric around the origin. In order for this to be an odd function, this either had to be -5 or this had to be +3. Odd, he says, what do I mean by odd? Odd functions have this property going for them. Odd functions are symmetric around the origin. If you turn it upside down, like if you reflect over the x, you get the exact same thing as if you'd reflected over the y. No, don't say the word inverse. Inverse means switch x and y. Algebraically, which is what Sage was actually saying, changing the symbol on the x has the same effect as changing the symbol on the y. Yeah, that's what it means to be odd. So for example, let me, for real, look. let's say here is, I don't know, 2 comma negative 3. In order to be odd, this point would have to be negative 2 comma positive 3. Changing the symbol on the x has the same effect as changing the symbol on the y. Now, do they have to always touch the origin? No, they just have to be symmetric around the origin. This one touches the origin, but it is not symmetric around the origin, so it can't be an odd function. It is an odd degree, but it's not an odd function. So that was just, a little bit of review and see what would happen. Okay. We've been told to factor and simplify, determine the values of x where we have a whole or a vertical asymptote. It doesn't say find the coordinates of the whole, so I don't have to find the y value. But we'll talk about how to do it. Because in the example below it, we will have to find the y value. So we might as well talk about it. Time to factor.
The top one is x plus 4 and x minus 4.
So Sage says he recognizes that the top is the difference of two squares. So it'll factor to a set of conjugates, x plus 4, x minus 4. And the bottom? The bottom, yes, there are two numbers that multiply to negative 28 that add to 3. Positive 7, negative 3, right? Negative 4, excuse me. Positive 7, negative 4. I told you, the last period was rough. You would think I didn't have a degree in mathematics.
How many degrees do you have? A degree in mathematics?
I have a degree in mathematics, that's it.
Does that mean you're an odd degree?
What does that? I have an odd number of degrees. Let me tell you what's odd. Let me tell you what's odd. You hush up, Max. Okay. Time to simplify. These x minus 4s will cancel off the top and the bottom. This function will simplify to x plus 4 over x plus 7. That means we do have a hole at what x value, Max? At x equals 4. Good. There is a hole at x equals 4 because I eliminated an x minus 4 off the top and bottom. So hold on one second. So I heard you, but if it was a number that made you divide by 0, but you were allowed to cross it off because it existed on top and bottom, you have a hole there. And one more question, and then I'll get to your question. If I know the x is 4, how would I find the y value at this missing point? Plug it into the simplified version. So it would be 8 over 11. Sage, what's up?
I was just going to ask whatever you factor out, like the opposite of that, like
the 0 of the factor is what we call it. Yeah. So it's
like negative 4 is equal to 0. Then you just
So what's happening is the thing I crossed off, you're saying what would have made it equal 0, so you just add a 4 to both. That's how you do it.
All right, cool. So it's just like,
Think about it as transformations.
Yeah.
Think about it as transformations.
Yeah.
This says shift left 4, right?
Yeah.
That means you went from 0 to positive 4.
Okay. So
I said that, but it says shift right 4, and you said yes. This is shift right, which means you went from 0 to positive 4.
So it's a whole because there's a multiplicity of 2?
It's a whole because it was a factor that was eliminated off the top and the bottom that had the ability to equal 0 on the bottom. So this doesn't have a multiplicity of 2. The multiplicities only happen for polynomials.
Okay.
Now, I mean, I don't even say it like that. We can't talk about bouncing and crossing for rationals, but no, it's not because it had a multiplicity of 2. It's because it existed on the top and the bottom, and I was able to eliminate it. And positive 4 no longer makes it equal 0. So that's what it is. If positive 4 could make the denominator equal 0 after it's simplified, that's a vertical asymptote. If it makes the denominator equal 0 before it's simplified, but not once it's simplified, then it's a hole in the graph. So like right here, don't look at the tops. There are two numbers that make the bottom equal 0. But once you're simplified, there's only one number that makes the bottom equal 0. So the one that's gone is where the hole is.
Okay.
Okay.
Thank you.
Mhm.
Like through that equation, how can you tell if it's a hole or a point on the graph? Because you said earlier that if you cross it out, it's either a coordinate.
Oh, no. What you're remembering yesterday was I was saying if the limit, let me just write it. Instead of just saying it, I'll write down what we were saying. I'm going to grab more of these IB notes and write all over them. Here's what I said. Let's say I give you no information about a graph. If I tell you this, the limit as x approaches, I'm just going to make up a number 1, okay? negative 1 of f of x equals 2, and I'm making up the number 2. We're just making things up. And I also tell you this. Either one of two things has occurred. Either there's a hole at the point 1 comma 2, but the reason why the limit is the same is because the graph was attempting to go to that y value, or the point 1 comma 2 actually exists on the graph. But you would have to know more about the stuff. Didn't apply to this one, yeah. And that's what I was saying in that question that we saw, as like we're going to have to assume that they wanted this to be a hole, otherwise the question's kind of a waste of our time. But yeah, so when you see, we call it a two-sided limit from the left and the right, if both sides approach the same y value, you either have a hole there or you have a coordinate there. Either way, it's going to have an x comma y. Our vertical asymptote, yes, we have one because, yes, there is still an x value that makes the denominator equal 0. There it is. Ta-da. All right. Let's put our skills from the entire sections, like 8, 9, and 10 together then, and do example 3. Example 3 says, factor, simplify, and do all this stuff, including a sketch. Factor, simplify, do all this stuff, and sketch. Write an equivalent form by factoring. What color pen do I want to use? I've used a lot of orange. Let me use blue. No, I can't write in yellow. You won't be able to see it. Yellow is only for special things. I'm calling some of you special, that's for sure. All right, there are two numbers that multiply to 12 and add to 7. 4 and 3. And yes, there are two numbers that multiply to negative 6 that add to 1. Positive 3 and negative 2. Hey, look. There's a factor matching on the top and the bottom. They cancel out. Go Gators, orange and blue. The x plus 3 cancels, leaving us with x plus 4 over x minus 2. We have written an equivalent form. There it is. This rational function does have a 0. Do I have a volunteer that knows where it is? Ooh, Ariana, you haven't talked to me yet today. At x equals negative 4. Now, how did we know that? He says, never mind. Okay. Because it makes the numerator equal 0. There it is. If it's a 0 of the numerator, it is a 0 of the function. As long as that's not where the hole was. We saw an example like that a couple lessons ago. 0 of the denominator is either a hole in the graph or a vertical asymptote.
And a 0 in the numerator is a 0?
A 0 of the numerator is a 0, also known as an x-intercept. Yes. So yes, we do have a 0, we do have an x-intercept, and it is going to occur at x equals negative 4. I'm going to go ahead and put a dot on x equals negative 4. Now it says to find x values where you have a hole. Well, you saw it right here in orange. I crossed off x plus 3. So there is a hole here. At what x value? Negative 3. It's the 0 of the factor that was canceled. So it's happening. I'm going to do the whole thing in blue so I can draw it in blue. It's going to happen at x equals negative 3. Here's the problem. I need to be able to sketch this graph. That means I need to know the y value of the hole in the graph. I have to take this negative 3 and I have to do what you guys told me to do earlier. I have to substitute it into the simplified version. I have to plug it in up here. I mean, I'll do it over here, so I got a little bit of space. So it's like negative 3 plus 4 over negative 3 minus 2. That is 1 over negative 5. The y value of the hole in the graph is at negative 1/5. Do your best. The 1/5 is going to be itty bitty bitty. So I'm just going to make the circle kind of large so it's hard to argue with me. Negative 3 comma negative 1/5 is here-ish. vertical asymptotes. Is there still a number that makes the denominator equal 0? Yeah, well, there you go. And we have a vertical asymptote. And it's going to be at the 0 of the denominator. X equals 2. I'm going to put that in red. This graph does have a horizontal asymptote. Gavin? At y equals 1. But how did you know that? That's the better question. How did you know that it was at y equals 1?
Because there is no multiple outside of the parentheses.
Because there's no what? I'm sorry?
There were like no multiples outside the parentheses.
So no number sitting on the front.
Yeah.
Okay, what if there had been like a number right down here? Well, let's just say I put a 3 right here. Then where would the horizontal asymptote have been? At 1/3, yes, but why?
Oh, because it's the ratio.
Because it's the ratio. There we go. So because the degree of the top and the bottom are equal, our horizontal asymptote is the ratio of the leading coefficients. And it happens to be a 1 over a 1 for this one.
If it's like a
Bottom heavy or top heavy?
it's like a 6 over a 3, would that mean the y equals 2?
Yeah, if the leading coefficient on top was a 6 and the leading coefficient on the bottom was a 2, as long as the degrees were equal, then it would be 6 over 2, or 6 over 3, which equals 2. Yeah. Now, if it's a top-heavy function, meaning the degree of the numerator is larger than the degree of the denominator, you have to use long division to figure out what your asymptote is. If it's bottom-heavy, meaning the degree of the bottom is bigger than the degree of the top, then you do have a horizontal asymptote at y equals 0 every time. So this one's horizontal asymptote is y equals 1. Remember, horizontal asymptote, well, how about we say it like this? Remember, an asymptote is simply a line that your graph will get infinitely close to. Asymptote itself does not mean you can't go here. It means you're going to get infinitely close to this. Now, can a graph ever exist at its y asymptote? Sorry, I was having a small stroke. Can a graph ever exist at its y asymptote? No, it can't. Why? How come? Because a vertical asymptote is an x value that makes you divide by 0, so it will never exist there. But can a graph cross its own horizontal asymptote? Yes, it can. And the reason why is because a horizontal asymptote is nothing but end behavior. That's all it is. It's describing what happens when x is remarkably back here or remarkably out here. That's all that's happening. It doesn't tell you anything about when x is relatively close to 0. So when graphs cross their own horizontal asymptote, it's often pretty darn close to x equals 0 because the end behavior just describes far left and far right. What this does is tell you as your graph goes to the far left or to the far right, it's going to flatten out towards the line y equals 1. That's what that means. Now, can this ever actually equal 1? No, because it has an x on the top and the bottom, and no matter what you do, the top number will always be 6 more than the bottom number. So you see, because it says +4 and this says -2. So there's no way this top and bottom are ever the same number. That's just not possible. So no, this one will never hit its y equals 1 horizontal asymptote. There we go. This says find the domain and sketch. I'm going to sketch it and then find the domain. But you know what would make it a little bit easier to sketch? More points. I have one point that it goes through and a hole it goes towards. How about we find a y-intercept simply because it's easy to do? When you're on the y-axis, what does x equal? 0. So let x equal 0. Look what you get. Boop! 4 over -2. So when x is 0, your y-intercept is -2. There. So now you just try to get close to the red dotted line. Bless you. Go through the dots. Don't go through the hole. Just like that. Well, that is a remarkably good curve, if I do say so myself. If you want more points, you are welcome to plug in other x values to the right of x equals 2, but it's just a sketch. Screw it. You're not going to see anything interesting. This will be its look. It'll look something like that. So domain is all that's left to do, and we're finished with this. By the way, this is an always decreasing function. See, it has no zones of increasing. It has no turning points. So no maximums, no minimums. Always decreasing. No symmetry as far as odd and even are concerned.
It's not increasing at the left one?
So it's never increasing because all of our curve pieces go from left to right.
Well, let's go.
Okay.
I was thinking like since that arrow is like going towards infinity, that way that'd be increasing.
Yeah, no, so you're thinking the x value is getting bigger, but the y values are always still falling towards this red dotted line.
No, I know that. I'm talking about the one.
This one you mean?
Yeah, that.
Yeah, but everything goes from left to right though is why.
Okay.
We always go from left to right like we're reading a book. Okay? So our domain then, it exists at every x value except for x equals -3 and x equals +2. So at -3 and +2, we string some stuff together with unions. I'm changing the color. There it is. How do we feel about that? Can you factor it and find all the pieces and parts? Yes. Okay, one person says yes. Thank you. Thank you, Chloe. All righty. If you can graph a rational function from an equation, you should be able to get an equation from a graph just by looking at the things that you have here. Let me tell you what I see. I see a vertical asymptote at x equals 2. Remember what a vertical asymptote is. A vertical asymptote is a zero of the denominator in its simplified form. That means it's also a zero of the denominator in its unsimplified form. Call this one f? Yeah, it's f of x. Since 2 is a zero of the denominator, there's an x minus 2 in the denominator. I also see a hole in the graph at x equals 4. What that tells me is x is not allowed to equal 4, so it clearly made the denominator equal 0. But since it's not a vertical asymptote, its factor must not exist in the simplified version. And the only reason why its factor wouldn't exist in the simplified version is if that factor, that is a 0 of, canceled out. So it's on the top and the bottom. What else do we know? We also know that this graph crosses the x-axis at -3. So this graph has a 0 at x equals -3. Zeros of rational functions come from the numerator. This is a 0 of the numerator, so x plus 3. And let's just make sure that it makes sense by looking at the horizontal asymptote. It's at y equals 1. Leading coefficient at the top will be a 1, degree 2 polynomial. Leading coefficient at the bottom will be a 1, degree 2 polynomial. 1 over 1 should work out perfectly. And just to make sure, I want to double check what happens if I plug in x equals 4 in this simplified version. Because I'm looking for a number bigger than 3 but smaller than 4. If I plug in 4 into that, I get 7 over 2. That's 3.5. Works perfectly. Yes, Max?
What would you do if the horizontal asymptote was 2?
So the only way that the horizontal asymptote would be 2 is if this 0 was also moved. So the 0 of the the 0 of the rational function is a dead giveaway to what's going on up here. So let's say for a second that the x-axis wasn't crossed at 3. Let's say the x-axis was crossed at negative 2.5. It's not, but let's just say it was. If 2.5 makes the numerator equals 0, you wouldn't say x minus 2.5. What you would say is 2x plus 1. You see? That's negative 0.5. Sorry. Negative 2.5. Is this 5 and 2? My apologies. I said negative 2.5, right? I am struggling. Struggle bus. Struggle bus. There you go. 2 times negative 2.5 is negative 5. Great. So if this thing crossed the x-axis at negative 2.5, it would force a factor in my numerator to be 2x plus 5. But look here. If this was on the top instead of this blue thing, what would the leading coefficient of my numerator be? A 2. And the leading coefficient of the bottom is a 1, which makes my horizontal asymptote 2. So you will use the 0 to figure out what the other factor is, and it will control the horizontal asymptote. They're related but unrelated. Yeah, like one will end up happening because of the other, accidentally almost. Okay? Does that clear it up? It's a good question. Anybody else? No? Okay. Okay. Next, we've already talked about them, but slant asymptotes, also known as oblique asymptotes. These are linear asymptotes, but they have slope. They're not horizontal. A slant or oblique asymptote occurs when the degree of the numerator is 1. Catch that? 1 higher than the degree of the denominator. That's what makes it a degree 1 in behavior asymptote. If the numerator is top heavy by 2, now you have a quadratic asymptote. If nothing cancels out. Quadratic asymptote. Okay? If the numerator is heavier by 3, cubic asymptote. Things like that. It just works like that. The slant asymptote is the quotient polynomial found by using long division. So like I said, if it's top heavy, you must use long division to get the equation of the asymptote. Just remember that that long division will usually result in a remainder at the end. Right? But because we're talking in behavior, which means the x's are going towards the infinities, the remainder will be a rational function that will always be bottom heavy, so it'll always go to 0. So when we do our long division, we disregard the remainder for the asymptote. Cool? Numeric long division, as if you don't remember how to do long division. I'm not even going to bother. We're just going to go right to the polynomial long division. What's that?
No, we're good.
Do you want me to do it? Yeah. Okay. All right. Hey, look, I will do it in case you need it for SAT. How about that? You're welcome. 14 into 482. 14 clearly doesn't fit into this 4. But 14 does fit into 48. Any guesses on how many times? 3 times. It goes in 3 times. 3 times 14 is 42. Subtract straight down. Then you're asking yourselves how many times 14 goes into 6. See how I dropped the 2 down? Now you're asking yourself how many times 14 goes into 62. It actually goes in 5 times. Wait, does it? No, it doesn't. That's 70. No, he was right. He was right. It's 4 times. I was thinking 12. 12 goes in 5 times. 14 goes in 4 times. 14 times 4 is 56. So we have a remainder of 6. No, it's not. Don't do that to me. I thought I was wrong. It is 6. Man, I was gonna believe you so fast. Did you hear how disappointed I was in myself? Yeah.
Isn't it 16 and 6 minus 5?
Yeah, but I have to borrow. I have to borrow. So our quotient, the quotient is 34. The remainder is 6. The actual answer is 34 and 6/14. Of course, that reduces. But did you know when you say 34 and 6/14, what you're actually saying is 34 plus 6/14? No, that's right. No, what I'm saying, did you know that that's what that means? That is why when we do the long division here, we put it plus remainder over divisor. That's why we do that. Now, I will tell you, when you're doing your homework, when you're doing your homework, I have given you a polynomial long division question that is missing terms. This is not missing terms. What do I mean by that? It counts down x to the 2, x to the 1, x to the none. But let's just say it was missing this x term. When I go to do my long division, I would have to have an x term represented with a 0x. Okay? I picked a question in your homework that has a missing term. I did it for a reason. I'm telling you right now, that means you have to replace a 0x squared and maybe a 0x or something like that. If it's missing, it has to be there. It has to hold the gap tooth smile open. Okay? Here we go. 2x plus 1 going into 6x squared plus 4x plus 5. I need this 2x to become a 6x squared. What do I have to multiply 2x by to get 6x squared? 3x. Take the 3x and multiply it to the 2x plus 1. Kind of like how you took this 3 and you multiplied it to the 14. Anyway, take this 3x and multiply it to the 2x plus 1. And what you'll get is 6x squared plus 3x. And then subtract straight down. What? Isn't it? Because it's 3x times 1? Yeah, don't scare me like that. I've been making too many mistakes today. I'll believe you too fast. I got an x here, a 1x when I subtract. And then I have to drop this 5 down, and it gives me plus 5. What do I have to multiply a 2x by to get an x? A 1/2. That's really weird, but it's true. It's really weird, but it's true. Plus 1/2. Now you multiply by 1/2, what you're going to get is x plus, well, that's 1/2, which is strange, but whatever. We're just going with it. 5 minus 1/2 is 4.5. Yeah, 4.5, which is 9 over 2. Whatever you want to say. Let's just say 4.5, whatever. Make our lives easy. So what is the quotient? The quotient is 3x plus 1/2, which is strange, but that's what it is. The remainder is 4.5. So what is the actual answer? The actual answer is 3x plus 1/2 plus 4.5 over 2x plus 1. That's the actual result. And that is a great place for us to stop today, especially since I didn't even do any of this back page with period 7 today. I only did the front. Yeah. So you guys were big time nerds, and they were distracting me.